This lesson is on something called the Lagrange error bound or the Taylor error bound. And this is what we're going to use if we don't have an alternating series. So essentially the remainder is what we call the error. So it's the difference between the actual function and what the polynomial approximation is. And it can be given by, at some point, the next term, sort of. So what we use is something called the Lagrange error bound, and I'm going to link in a video for where the derivation for where this comes from. So we have this formula: the remainder, or the error, is m times the absolute value of x minus a n to the n minus 1 over n minus 1, or n plus 1 factorial. The m is going to be the maximum value of the nth plus 1 derivative for some value between x and a, and we're just calling it c. Okay, x is the given value. A is going to be the center. So in order to use the Lagrange error bound, you have to be able to come up with those three pieces of information. So let's see how this works. We're going to use Taylor's theorem, also known as the Lagrange error bound, to determine the accuracy of the approximation E is approximately 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial. So this is the Taylor series centered at 0, but we're evaluating it at 1. So we're looking for how far off this approximation is. Well, our error bound is going to be less than or equal to m x minus a to the n plus 1 over n plus 1 factorial. Okay, so let's investigate this m, the maximum value of the derivative. Well, f of x is e to the x. So f prime of x would equal e to the x, and so on. Well, if I think about e to the x between 0 and 1, it's going to reach its maximum at 1. So this would be 1 e to the 1, or just e. So my maximum value is going to be e in this case. My value is 1, my center is 0, and if this is to the third, then my n plus 1 is going to be to the fourth. Okay, so that is the maximum value. You could then plug it in your calculator or just leave it as e over 4 factorial. Okay, now we're going to determine the degree of the polynomial required for the approximation of e to the 0.1 for the error to be less than 0.001. Well, the error, just like the last one, the maximum value of the derivative is going to be e. My value is 0.1. We're subtracting 0. The n plus 1 over n plus 1 factorial. So I'm just going to put this in a chart. Put degree over here and the error over here. Okay, so my smallest degree would be 0, but let's go ahead and check 1, which means my error, my maximum value would be e to the 0.1. So we're going to have e to the 0.1 times 0.1. If our degree is 1, this is going to be 2 over 2 factorial. And if this ends up being too big, we can go back to 0. 0, 0, 5. Okay, so that's bigger. So then we're going to go to the next one, 2. So it's going to be e to the 0.1, 0.1 cubed over 3 factorial. Using the calculator to get 0.00018, which is less than 0.001. So our solution is going to be degree 2. So we said we've increased in accuracy the higher the degree of the polynomial or closer you are to the center. Which leads us to our next example that says determine the values of x for which e to the x can be approximated with our degree 2 polynomial 1 plus x squared over 2 factorial if the allowable error is at most 0.0005. So in general, my error is going to be less than or equal to the maximum value of the derivative is going to be e to whatever x is. X is my value minus my center 0 to the n plus 1. Oh, sorry. We know this. If this is 2, this is cubed over 3 factorial. Okay, that's what our remainder, our n plus 1 is 3. So we're looking for e to the x times x cubed over 3 factorial to be less than 0.0005. What I'm going to do is graph these two things. We actually want this to be less than the absolute value. So I've put this in my calculator, the e to the x times x cubed over 6. I put the positive 0.005 and a negative 0.005. And then I'm going to graph it. And we're going to find each of these intersections. So I'm going to calculate the intersection between the blue curve and the black curve, which gets me negative 0.151. And then the intersection between the blue and the red, which gives me 0.1377. So for those values, our accuracy is going to be between 0.0005. Okay, so if 1 plus x squared minus x squared over 2 plus x cubed over 6, if our fourth derivative is less than 1.5 for all values between 0 and 0.4, what is the maximum error for f of 0.4 using this third degree approximation? Yes. So my m is going to be 1.5. We're centered at 0, so 0.4 minus 0. If this is third, our degree would be to the fourth over 4 factorial. When you type that in the calculator, you get 0.0016. So our answer is B. Okay, let f of x be a function approximated by a Taylor polynomial. If the nth derivative is less than 1, what is the minimum number of terms for the Taylor series centered at x equals 2 that are necessary to sum up to approximate f of 2.5 with an error less than 0.00001? So our remainder is going to be less than or equal to, my m is going to be 1. We're going to have 2.5 minus 2 to the n plus 1 over n plus 1 factorial. So this is going to be 0.5 to the n plus 1 over n plus 1 factorial. So I'm going to be plugging values into here, and I'm just going to guess and check. I'm going to put terms, degree, because those are going to be different, because if I have a degree 0, I have one. If I have it one term, that's degree 0, and so on. And then my error. Okay, which is going to be 0.5 to the n plus 1 all over n plus 1 factorial. So I'm going to jump to maybe say 3. So if I have 3 terms in my series, the degree is going to be 2. Okay, because I'm going to have a constant, a linear term, and a cubic term, so 3 terms, but it's going to be degree 2. So my error is going to be 0.5 cubed over 3 factorial, which is 0.021. I'm going to continue to do this. So let's try 4, which means we have degree 3, which means our error is 0.5 to the 4th over 4 factorial, which is 0.002. So we're getting closer, but we're still pretty far off. So this is just going to change to a 5 and a 5 factorial. So we get 0.0002. 6 and 5 gets me 0.00002, so we're close, but that's still a little bit bigger. So 7 terms would be a 6th degree polynomial. My error would be 0.5 to the 7th over 7 factorial, which is 0.000015, which is less than what we're looking for. Okay, so we have to have 7 terms in order for the accuracy to be that good. Okay, so let's look at an AP problem. So we have a function has derivatives for all orders for all real value x. Then it gives us f of 2, f prime of 2, double prime, triple prime. So we're going to write a 3rd degree polynomial for f about x equals 2 and then use it to approximate 1.5. So our 3rd degree polynomial is going to be f of 2 plus 5x minus 2 plus 3 times x minus 2 squared over 2 factorial plus, actually, minus 8x minus 2 cubed over 3 factorial. Then we're going to plug in 1.5. So we plug in 1.5 for our x. Usually I'd leave it like this, but we're actually going to have to use this in the next step. So negative 4.9583. Okay, in the next part it says the 4th derivative of f satisfies that the absolute value of the 4th derivative is less than or equal to 3 for all x in the closed interval 1.52. Use the Lagrange error bound on the approximation of f of 1.5 and explain why f of 1.5 does not equal negative 5. Okay, so plugging it into our error. Okay, it's going to be less than or equal to, my m is 3, and then we've got 2 minus 1.5 to the 4th over 4 factorial, because we've got a degree 3, so it's going to be 1 higher than that. Okay, this gives me a value of 0.00781. So our approximation has an error of 0.00718. So if I take my value here, negative 4.9583, and I subtracted an error of 7.81, we get negative 4.966, which is close to negative 5, but it's still greater than negative 5, and this is the maximum the error could possibly be, so it can't be negative 5. Okay, now we're going to write a 4th degree Taylor polynomial p of x for g of x equals f of x squared plus 2 about 0. So I'm going to take this and plug in x squared plus 2 for those. So we're going to have negative 3 plus 5 times x squared plus 2 minus 2 plus 3 x squared plus 2 minus 2 squared over 2 factorial, which is going to get me my 4th degree that we're looking for. So this is going to be negative 3 plus 5x squared plus 3 x to the 4th over 2 factorial. So there's my 4th degree polynomial. And why does it say g has a relative minimum at x equals 0? Well, the pieces of information we can get from this any general Taylor series is f of 0, f prime of 0 times x plus f double prime of 0 over 2 factorial, and so on. So here's what we can get from this. If there's no linear term, that means f prime of 0 is 0, which means we have a critical point. And I know that the second derivative, sorry, rather this should be g for this case, g prime of double prime of 0 is greater than 0, which means our graph is going to be concave up, which means if it's 0 and concave up, we have a relative minimum from this information. So that is the Lagrange error bound. It is kind of an abstract idea, but we'll use either the alternating series bound or the Lagrange error bound to approximate error.